Okay, so just wanted to write down. Okay, so just wanted to write down for current. Okay, so just wanted to write down. Okay, so just wanted to write down both the equations for current only when the transistor is on. The transistor is off, don't have to care about the current equation. And this is the only current that we are going to calculate in this course. Okay, and almost throughout the world, if anybody is doing any hand calculation, okay, that is they are using some equation to calculate the current, this is the current that we calculate between the drain and source. Okay, that is the first thing. And then we discuss the different modes of operation within on itself. Okay, this is again for Nmos, and the equation is here, and in this whole equation, this term, whatever is within the bracket, the W by L is our friend. This is the only thing we can use to increase the current. We never want to decrease the current. Whatever value, for example, if some circuit is made with some default value of W, okay, L, I said before also, we don't have to fix anything. Always the L will be fixed based on the technology. We don't have to vary it at all. And we don't want to increase the L, because if I increase the length, the current decreases, and with that we never want to see that. So the W, okay, which effectively is the W by L, is the one that we can change. So this is the current flowing through. We derived this equation. Just one thing, in the beginning of the equation, QC equal to, we had to start with this. I started with just VGC, okay, Q equal to into C ox. And the reason why VGC minus VT, if you remember the definition for VT, VT is the amount of voltage required to attract some concentration of electrons. And anything beyond that, okay, we always want that much amount of electrons to be there, so that the region is inverted and the transistor is on. That is, the connection is there. Beyond that, whatever is attracted, that can be used for the conversion. That is why we have to start with this expression. If you start with this expression, then go through the rest of the derivation. The steps are the same that we did yesterday. Only thing is, I forgot to put this minus VT here inside this expression. So if you put this VGC minus VT into C oxide, you will end up with this minus VT everywhere. And we start with this and then slowly modify it. Sorry. Very small modification to go from linear to saturation. We change the VDS. Okay, the VDS, because it saturates, the VDS gets stuck at VGS minus VT. So if you put that in this equation here and here, you will end up with VGS minus VT, the whole square, divided by 2. That divided by 2 I have put. So this is the equation that you have to use for current, for current calculation. Okay, and we have derived this equation. The derivation is important. We'll also see some numericals. Okay, so before going, just a small true or false quiz, just to understand. Okay, 1, current Okay, first question, current is more in linear region, true or false? So we have the equations, you can look at the equations, but this is in general, okay, just for some particular power supply voltage, some particular transistor. Suppose I'm calculating the current for linear region 1, saturation region 1. I will find that the linear region current is actually lesser, because if you remember the curve, the first part of the curve is the linear region, then it goes to saturation. So linear region, the magnitude at least, of course, because if it's a PMOS transistor, it's in the third quadrant. Let's not worry about that. The magnitude of current, okay, that is the amount of current flowing, is always more when we are talking about the saturation region. So definitely this is not true. Okay. Second question is little bit more interesting, little bit more challenging also. Nmos current is less than Pmos current. Okay, we have two types of transistors, Nmos and Pmos, and both of the transistors current will flow definitely. And again, we are only talking about the magnitude. This is not a trick question where one current is in first quadrant, another current is in third quadrant, fine, etc. It is just the magnitude of the current. Okay, so Nmos current and Pmos current we want to compare, and obviously everything else is identical. That is, the power supply is identical, the W by L is identical. So if we look at this equation, okay, assume that both are in saturation only, somehow we have put that in place, and let's say we are looking at only this equation. Okay, look at all the terms in the equation. We will start from here. Assume that this is the same VGS minus VT, because it's power supply, we can assume it's the same VT. We can assume that both the devices have the same magnitude of threshold voltage. W by L, we can set that, assume it is the same. Then we have mu COH by 2. Now mu and COH, we said they are material parameters, but here is the first difference between NMOS and PMOS. C oxide will be the same for both transistors, because C oxide, as we will see in the numericals, it depends on the silicon, okay, and the thickness of the oxide region, and that will be the same because they're all made in the same technology. I can't make one transistor in 180 nanometer and another transistor in 90. It's just not possible. So the only thing that is remaining is this mu. Mu is a, we said it's a physical parameter, definitely yes. But now that we are talking about NMOS versus PMOS, the mobility is of the charge carriers. And since the charge carriers are different, the mobility is also going to be different. And this is not easy to guess, of course. Electrons and holes, okay, they are identical except for the opposite polarity. And also the mobility for electrons is much higher, because electrons, if I apply a voltage, they will move. But holes, the problem is every time a hole has to move, it has to break a bond. Because what is the meaning of hole? It is the absence of an electron. So if a hole has to travel, electron has to jump from that atom into this hole. So that effectively means the hole has traveled, and if electron has to jump, obviously the bond has to be broken. So the mobility of holes is lesser, not as good as electrons. So because of that, okay, NMOS current is generally, if all the other parameters are the same, I have two devices, NMOS and PMOS. The NMOS will be giving me a higher current. Okay, so this is also false, and we will talk about other properties of current also as we go on. But for now, let us just try some numerical. Since we have a equation, okay, it is natural to try a numerical, and I'll try to leave these, but this equation is covering the whole board, so we will just leave. Okay, so let's start with the NMOS device, and Okay, so we have one more parameter is required. Okay, so I hope all the parameters are there. We will see Nmos transistor, mobility. Okay, mobility is my variable mu in particular. Since it is a Nmos transistor, this mobility is nothing but mu n. Okay, mu n is the mobility of the electrons in the transistor. Threshold voltage is given as 0.4 volts, and Tox is given as 10 angstrom. And this is a situation where the gate source voltage is fixed at 2 volts, and we want to calculate the current for three different values of drain source voltage. So one thing, the physical parameters, there are some physical, there are some electrical. Okay, and generally we will try to group all the physical parameters and keep the value fixed. So for example, in this case, okay, mu into C oxide into W by L. Okay, these are, so again I see W by L is not there, so let us add that here. Okay, the physical parameters, meaning the parameters that depend on the device and not on the terminal voltages, they are mobility mu, C oxide and W by L. So for a transistor, after the fabrication, this is always fixed. The only things that can change are the electrical parameters. Even this is fixed, okay, but since this comes inside the current equation, we can't use this directly. But whatever is the outside of the current equation part, we will group all those together and call this as beta. Okay, some beta. The advantage of calling this as a separate thing is we can calculate this and keep, okay, and reuse this again and again, because the current equation, this term is there in all the current equations, that is both in linear and saturation, this particular term is there. So if I can calculate this once, I can reuse this again and again for the transistor. So first we will calculate this value. Okay, this is equal to, first we will maybe calculate C oxide because that is itself not there. Now one thing to remember, okay, we have a equation for capacitance which is A epsilon naught by D. But if you remember, as we were coming through the derivation, the A part, okay, we expanded that as W into L and we cancelled it out with one L and we ended up with this W by L. So you don't have to put A into epsilon by T, that will become a mistake. Okay, so when we are calculating this oxide capacitance, C oxide, it is just epsilon oxide by T oxide, and this again, like I said, 3.9 into, okay, epsilon naught into epsilon r, and epsilon r is 10 power minus 14, that is 8.85 into 10 power minus 14, okay, divided by now 10 angstrom, that is 10 into 10 power minus 10 meters. Okay, but remember all our calculations for this, that is why I have written these units also. All the units will be in centimeters. So if I put it in meters, I will be making a mistake. I have to make the conversion from angstrom into centimeters. So 10 power minus 8 centimeters. Okay, and this is the first part. So if I calculate this, I will get, okay, so 3.45 into 10 power minus 6. Since this is capacitance, the unit is farad, but it is farad per centimeter square because the A part is not being used here. The A part was taken as other terms in the equation. So this is my C oxide, okay, and then I can multiply it with mobility. Therefore, beta equal to, okay, mobility is given as 130 into C oxide, which is 3.45 into 10 power minus 6 into W by L is 4. Okay, so I'm getting 1.79 into 10 power minus 3. So this is the value of beta. So I will just write it in that side. Okay, beta equal to 1. Keep this for now, okay, and as you know by now, steps are important. So all these individual steps will also help you even if the final answer is not correct. So these steps will also help us in making the calculations easier because again and again they will come. So now we have the first part. Let us go for the actual terminal volt. Up till now we don't care about the terminal voltages, okay, whatever they are, that component is required. Now we will go for the terminal voltages. Let us go for part A, okay, and as always, first find out what is the mode of operation. Only when we find the mode of operation, we can go for the current calculation. So mode of operation, we need to put in all the values. Okay, so VGS minus VT I am getting as 1.6. Of course, I have already determined that the transistor is on because VGS is 2 volts, right? 2 volts is greater than 0.4 volts, so definitely the transistor is on. I don't have to check that. Once the transistor is on also, it can be in linear or saturation. So first I am getting 1.6. So VGS minus VT compared with, okay, definitely 1.6 is greater than 0, which means that the transistor is in the linear region of operation. Okay, so once I have determined it is in the linear region of operation, then I can calculate the current, and I am calculating the current in this case even though I don't have to, just to show you, okay, what is the final answer going to be. Some of you might already know the answer even without the calculation, even without using beta, etc. For this A case, you might know the answer, but we will still put the numbers and see what it is going to be. So therefore, IDS equal to, okay, mu n Cox into W by L. That part already I will have it as the beta into VGS minus VT 1.6, okay, VGS minus VT minus VDS by 2 into VDS. This is why when VDS equal to 0, even if the transistor is on, okay, the current is still going to be 0 because the whole thing gets multiplied by 0. The current cannot flow. There is no flow in the horizontal direction unless there is a drain source non-zero voltage. 0 voltage, it will not flow. First case is very easy, 0 amperes. Okay. Now let us go for the second case. So VGS is not changing, it is still 2 volts. So this stays true. Now VGS minus Vt, and I have to compare it with till it is greater. So continues to be in linear region of operation, okay, but this time definitely a non-zero value of current. So let us calculate the value. Therefore IDS equal to beta, which is 1.79 into 10 power minus 3 into VGS minus VT 1.6 minus VDS by 2 into VDS equal to, so this is just 1.6 minus 0.5 into 1, so 1.79 into 1.1. Okay, so 1.974 milliamperes. This is the value of the current, and this generally is important number because most of the numericals that you will see, they are going to be taken from realistic situations, that is the T oxide, the power supply. Nowhere you will see suddenly power supply of 100 volts. 100 volts, I don't think it has ever been given to any transistor ever, okay, not since the beginning of the CMOS devices. And the same way the threshold voltage, it will be anywhere around 0.5 volts for Nmos, minus 0.5 volts for Pmos. There are no other values. So these are all what are called as physically significant values, and that also means that the numbers that we get for current, okay, should be correct. And the main reason why things could go wrong is because of the centimeter to meter confusion, okay. And if you don't do that, either go in one direction, that is instead of 1.974 millimeter, you might end milliampere, you might end up with 100 times more, that is you might end up with 0.19 ampere. 0.19 ampere in a single transistor of these sizes will immediately burn the transistor. It's just too high a current, so that's not going to be realistic. And the other direction, suppose instead of 1.974 milliampere, suppose you do something and you go to microampere, okay, maybe 100 microampere you might get in some situation, but 1 microampere is a very small current also. So hopefully we stay in the range of milliampere to microampere. Anything below 1 microampere you have to recheck the calculation. So that is why the numbers that we get for the current are also important, okay. So this is the first case, 1.97 looks okay, so we can move on to the next case. Sorry, I should have erased this. It was part B, not part A. B, and then this will be part C. Okay, so part C, again the top stays the same. Now what, again same things to compare. VGS minus VT equal to 1.6 and VDS equal to 2, and now this is greater. VDS is finally greater, which means this has gone into the saturation region of operation, okay. So saturation region of operation, we have the new equation for current, IDS equal to mu Cox by 2 W by L VGS minus VT the whole square. This is the equation we derived yesterday, but I have done a lot of these calculations there, okay, in terms of beta. So this is equal to beta by 2 into by 2. Why by 2? Because I have mu n Cox WL by 2 here. So I can directly reuse that number equal to 1.79 into 10 power minus 3 by 2 into, okay, now VGS minus VT, I have the number 1.6 the whole square. So if I calculate that, I will get 2. 2.29 milliampere. So this is the current that is flowing through the transistor in the saturation region, and it also satisfies our general knowledge that current is more in the saturation region as compared to the linear region. So it can from 1.97 to 2.29, and you can have a few more parts. Suppose, okay, your problem is having one more part, D VDS equal to 3 volt. Okay. After doing this part C, directly for part D also, I can write this directly. How can I write this directly without doing any calculation? Because that is the meaning of the saturation region. In the saturation region, if you remember, the current is a flat value. Okay, VDS is the x-axis. VDS keeps changing, but the current stays at the same value. Because in this equation also, okay, this is the equation for all of saturation region, and in all of saturation region, the current equation does not have VDS, which means that it is going to stay at the constant value. What is that value? We have just calculated. So for different values of VDS, if it is given, okay, very quickly you can write it off. The same value will continue. It will be at the same value. So this is the example of current calculation with Nmos, and we will do one more numerical where we are going to do the current calculation for the Pmos transistor.
Negotiation ಎಲ್ಲ ಆಗಿದೆ but one more partner is there to solve the I'll find out that one. We still can get one or two more votes, especially Karnataka and the they didn't need
So PMOS transistor, the conditions are all reversed. Okay, on is off, linear is saturation. Both the conditions are reversed. So physical parameters are given. So here also we will do the same thing. We will calculate beta. Okay, beta equal to mu p into same thing, C oxide equal to epsilon ox. So here also nothing is given about epsilon or epsilon R. So we will always assume it is silicon dioxide, which means the relative permittivity is 3.9 into 8 divided by, okay, this time the T oxide is in nanometer. So nanometer is 5 into 10 power minus 9 meter. Okay, but as always we don't want to stay in meter, we will be in centimeters. Okay, so 5 into 10 power minus 7 centimeters is 5 nanometers. So this is my C oxide. If I calculate this, I will get, okay, 6.903 into 10 power minus 7 farads per centimeter square. This is the C oxide. So therefore beta P equal to, mobility is 70 into C oxide into W by L is given as 10. So that is equal to into 4.83 into 10 power minus 4. So I will write that here, beta equal to 4.83 into 10 power minus 4. And can someone think about what are the units of this beta? We have been putting units for everything, right? Beta also should have some units. It's not a dimensionless constant like W by L, for example, has no units. But beta units, it is difficult to imagine what is the units directly, but indirectly, if you see the current equation, it is I equal to beta into voltage into voltage, that is VGS minus VT minus VDS into VDS, or VGS minus VT the whole
This
square.
is yes, madam.
That is beta. If you do the dimension analysis, if you cross multiply, it should be ampere per volt square, so that it will get cancelled and you will get ampere. Okay, so that is our beta. So once I have that beta, I will just keep it there for now and calculate first the region of operation, then we can calculate the current. So we'll start with region A. Okay, and here also we have to compare VGS and VT. Okay, so VGS for region A is 0 volts, 0, and VT is minus 0.4. So VGS is greater than VT. That is clear, right? Positive number, negative number. Positive numbers are 0, and then you have negative numbers, means obviously 0 is greater than the negative numbers. So VGS is greater than VT for case A. And if this was a Nmos transistor, the transistor is on. But this is a Pmos transistor, okay? Which means that the transistor is off, and that also means that directly I can write there is no current flowing. For all practical purposes, drain source current is 0. Very simple case. The transistor is off, current is 0. Okay, that is case A. Now let us go to case B. VGS now is minus 0.5 volts. Okay, and VT is the same value. VT is still minus 0.4. So minus 0.5 minus 0.4, definitely it becomes true, right? This condition now becomes true because minus 0.4 is greater than minus 0.5. And if VGS is lesser than VT, the Pmos transistor is on. Okay, this is what we have to remember. The conditions are opposite that of Nmos transistor. Pmos transistor is on. So once it is on, then we have to calculate the region of operation. Only when we calculate the region of operation, we will be able to calculate if it is in linear or if it is in saturation. So that we will do by comparing VGS minus VT. Okay, that is minus 0.5 minus of minus 0.4 equal to minus 0.1. This is my VGS minus VT. Okay, even though VT is having negative symbol, I should put that also. So minus 0.1 and VDS is sorry. See, I did a mistake. Okay, VDS is minus 1. VGS minus VT is minus 0.1. So which is greater than which? Definitely VGS minus VT. Minus 0.1 is greater than minus 1. Therefore, so I can write that as VGS minus VT is greater than VDS. This is VGS minus VT greater than VDS is saturation for Pmos. It is opposite. Not only did the on-off conditions get reversed, okay, the linear and saturation condition also have gotten reversed. So this condition for a Pmos transistor tells us that it is in saturation mode of operation. Now finally I can calculate the actual current. So then I can remove all this. Okay, so therefore IDS equal to mu P C ox by 2 into W by L into don't change the saturation current equation. Saturation current equation is always the same, what we see here. Okay, only the conditions for saturation are different. If we have determined that it is in saturation region, use the saturation condition. If you switch both, then again you'll be doing a mistake. So be little careful. If you change everything, then that is also a mistake. You have to change half the things, don't change half the things. Okay, so saturation current equation. So this is equal to, we will reuse our beta, 4.83 into 10 power minus 4 divided by 2 into VGS minus VT the whole square. So VGS minus VT the whole squared is here. 2.41 into 10 power minus 6 ampere. This is the current. Okay, so this is the current for part B. So we will continue with part C on top here. Okay, so again, if you just compare VGS minus VT with VDS, we see that it is still lesser. That is, VGS minus VT is greater than VDS, which means it continues to be in the same conditions here and here. Okay, even though the value of VGS has changed, it is still not in linear mode. And to be in linear mode, it will have to go even higher. So if you want, you can try this later. If you assume VGS equal to minus 1.5 volts, okay, then it will go from linear into saturation into linear region of operation. So this is a good exercise. You can try this yourself. Okay, this current is the same. I don't want to calculate this again because since it is in saturation, the current stays the same, right? 2.41 microamperes. You can try this. Let us see what is the current. Okay, and see what is the current for linear region, and more importantly, I want you to compare it with 2.41 into 10 power minus 6. Okay, according to our this thing, it should be lesser. That is, the magnitude should be lesser in the linear region, and that is what I want you to verify. Try it for one more case. VGS equal to minus 1.5 volts, and see what you get for the value of current. Okay, so this is some examples. When we get closer to the internals, we will pick up more examples and do. But this is the general this thing of current calculation. The most important thing to remember is first be clear which device it is. Okay, since we have two different devices, Nmos and Pmos, there are two different conditions. That is, the condition for linear is also reversed. The condition for on and off is also reversed. That is the first thing. The second thing is, once you have found out whether it is on or off, if it is on, then definitely you have linear and saturation. You have two more regions. You have to find out which is the region. And the main equation, always what we will compare is VGS minus VT and VDS. Always we will compare this only, Nmos or Pmos, doesn't matter. Okay, and always the condition for Nmos, remember that clearly. Okay, remember one set of condition for on, linear, saturation. If it is Pmos, reverse all the conditions, then you will get the correct conditions for Pmos. And at the end, there are two separate equations for the current also, one for linear, one for saturation. There also we can use a little simplification. Remember the linear equation, the longer equation, you remember it properly. Okay, and whenever you want to go from linear to saturation, from that, in that equation, wherever you have the term VDS, if you replace that with VGS minus VT, you will get the automatically the simpler equation, which is the saturation equation. Okay, so you don't have to remember everything, just have some tricks which will help you remember fewer things, but you will be able to solve all the general class of current calculation. So this is one set of problems. Another set of problems is they might, but it's a little more complicated. Given the current, okay, that is you have some current value, you might have to calculate the voltage. That is sort of going in the reverse direction, and it is not very practical also, because in digital circuits we always have the voltage because we have only two voltages, right? So you always have the voltages, we just want to calculate what is the current. So these types of problems are more common. That is, given the terminal voltages, calculate what is the current flowing through the device. So it's almost time, I think. Okay, so we have a couple of more minutes. So see if I can find out some more questions to test our understanding of this current flow. Okay, so first question. Okay, now some things we cannot change, that already we have discussed. Okay, very rarely you will see circuits today with multiple power supplies, meaning we have different values of VDS. Very rare. You will not see any circuit where one side of the circuit the power supply is 3.3 volts, other side it's 2 volts. It creates too much of what can I say? It creates too much of interconnection between the different levels of voltages and too many issues because of that. So generally the power supply is the same. But we did say that the threshold voltage, okay, can be varied. That is, during the fabrication or in the fabrication itself, some transistors might be made with a different value of threshold voltage. And the question now to you is, what is a better value? Okay, that is, higher value of threshold voltage is lower, higher value is good or lower value is good. And what you have to remember is current. Okay, always higher current is good. That is, if anybody is looking to improve the performance of their circuit, their transistor, which in turn improves the circuit performance, in this case we are talking about the speed. Okay, if I'm wanting to improve the speed of my circuit, I always want more current. Okay, so that is the first thing to remember, most important thing. More current is always better. Given that condition, okay, threshold voltage, do I like a higher threshold voltage or a lower? And we are talking about magnitude because we have two types of transistors, Nmos and Pmos. Do I want a higher magnitude of threshold voltage for my devices, or do I want a lower magnitude of threshold voltage? That is the question. And how to answer this question? Very simple. Just see where it comes inside the equation. Okay, VGS minus VT. Wherever VT comes, it comes with VGS. It comes as VGS minus VT. And for the NMOS transistors, VGS is going to be positive, VT is going to be negative. So VGS minus VT term, that is directly proportional to the current. So if you want the current to go high, VGS minus VT also should go high. But VGS is fixed because that depends on the power supply, right? That will be 2 volts, or some, if you set it at the maximum value, it might be 2 volts. So we cannot change that. So VT, if I reduce that, then current will increase. So threshold voltage, if you reduce, so for example, we talked about NMOS transistor, for example, with 0.5 threshold voltage. If you can somehow, through fabrication, that can be done, it's not impossible. Okay, if you can make that into 0.4 or 0.3, your current will increase. So if I have two transistors, one with threshold voltage 0.3, other with threshold voltage 0.5, the 0.3 transistor is actually going to be faster. Okay, given everything else the same, okay, all other properties, W by L, power supply voltage, everything else the same, the 0.3 threshold voltage transistor is going to be faster because it can drive more current. That is the main thing. Because it can drive more current, it can either charge or discharge the node faster. Okay. If you do the analysis for Pmos also, you will get the same thing. Only thing is, in Pmos, VGS already is negative. So minus and the magnitude, if it is smaller, right, then that overall term also will be higher because it's getting squared. So because of that, for VGS, for Pmos or Nmos, it doesn't matter. The threshold voltage, if it is a smaller value, it is better. So that is the question. Does current increase with VT? No. Lower. Okay, so there's not much variation possible, but there are some tricks, and this is one of the more expensive ones to increase the current. The most direct one and the most accessible one to engineer is of course the W by L. If you can increase the W by L directly, we see in all the equations mu n C ox into W by L. W by L is there in the beginning of every equation. So the current is directly proportional to W by L. Most important thing to remember, if W by L increases, current also increases. Okay, so that's a good thing. Then you might ask me, then what is the limit? Why can't I, every transistor I make, okay, why can't I keep it at the maximum possible value, right? That is W by L has some maximum value. We saw one example where in 180 nanometer technology, W by L, W maximum value is 50 micro and L is 180 nanometer. Why can't I keep everything at maximum value? What is the problem with that? Okay, what is the possible bottleneck there? It's a valid question. Why do I ever have to reduce it? Okay, keep all the transistors at the maximum performance. The direct answer to that is W directly is a measure of the size of the transistor also. L is the measure of the size, W is also a measure of the size. So if every transistor is at maximum size, suppose your design requires 10,000 gates, you might hardly be able to fit 200 gates. You cannot do anything. Okay, so the